need to review before we jump into the practical section. How can I? Okay. And I have to start stirring. Okay. Today we just focus on chapter 33, the nature and propagations of light. Okay. So the objective of this part is light. Okay. So first you have to understand what is the light and property of light. Okay, and then the next step is when you understand what is the light, you will see how it interacts with another kinds of materials like eyes, like lens, and so on. Okay, like mirrors. So what is the light? So that's a pity that you have no chance to learn about the electromagnetic wave from the textbook. I hope you read a little bit about it. Where is my pen? Okay. So what is the light? Light is an electromagnetic wave. Okay. Or they can call it EM wave. Okay. EM stands for electromagnetic okay, wave. And you can see that here, this axis is for the frequency of the wave, and this is for the wavelength of the wave. Okay, and when you increase the frequency, you will reduce the wavelength of the wave. Okay, so tell me the relationship between the wavelength and the frequency. Someone please. Because it is a wave, so it have this form, right? So how can you determine the wavelength of a wave? You learn about the mechanical wave, right? So how you can determine the wavelength of a wave? Wavelength equal v velocity multiplied by because we learn from the mechanics that wavelength here is the path, the distance, right? And here is the velocity, so multiply by time. Okay, the time you finish one period, or maybe it will be equal velocity multiplied by 1 over f. Okay, and for the light in the vacuum, the velocity is c. Okay, keep in mind that c is the velocity of light in the vacuums. If the light in another mediums, the velocities will be different. Okay, and the way you determine the wavelength is between two peaks here of the wave. Okay. In fact, when we talk about the light, keep in mind that the electromagnetic wave consists two components. Okay, it have two components. The first component is propagations of electric field. Okay, and the second propagations is magnetic field. Okay, if you have time, please take a look at the chapters, maybe 32. Okay, they talk about the electromagnetic wave. Okay, so what does this mean? It means that when you want to describe electromagnetic wave, keep in mind that they have two components. The first is related to the propagations of the electric field, and the second one is magnetic field. Okay, and they are perpendicular to each other. They are in phase and so on. Okay, and I will draw one of them. Okay, so here is the z-axis. Here is the x. Here is the y-axis. Okay. So in fact, here is the electromagnetic wave. Okay, for example, here is the propagations of electric field. Okay, in the z-o-y plane. Okay, here is electric field. Okay, you see at different positions, the magnitudes of electric field is different. Okay, different in magnitude and also in directions. Okay, here is the propagations of the first components of electromagnetic wave. Okay, the second component is magnetic field. Okay, if I plot it like this, it should be in x-o-y plane, and it's like that. Okay, so here is B field. Okay, and you see that here, the magnitude of the B field at any position is different. And okay, you see here is the B field, here is okay. So if the E field and the B field like that, so the directions of the lines moving in this direction, here is the direction of V or C. C for the velocity of the wave in the vacuums. Okay, B field and E field. But normally when you learn about the optics, later you will see that we just normally consider the interactions of the light with other materials, just care about the electric field components. Okay, so normally we just use these components to describe the light in this section. Okay, in this course. But keep in mind that electric field light have two components like that. Okay, and the direction of V is in fact is equal. The direction you can determine is like that. The direction, I just care about the direction. Okay, okay, determined by these products, cross products E and B. Okay, you can use the right hand to determine it. Okay, I guide you how to determine this before. Okay, so light is an electromagnetic wave. Okay, and it shows particle property as well. Okay, why? Because some phenomena, if you just use the wave properties, you can't explain it, like photoelectronic effects. Okay, we have to use the particle property to explain those effects. Okay, and we call that the light have the dual properties. Okay, wave and particles properties. Okay, so now you understand what is the light. Okay, some properties of the light. So let's move to the next step to see how we describe the wave. Okay, so here I have two kinds of source of light. The first one is point source like that. Okay, the second one is on the second figure like this. Let's see. Let I move this a little bit. Okay. Okay. So if you have an electromagnetic wave like this, okay, normally we just use electric field components to describe it like this, okay. Use here is a way to describe the light, okay. Here is the first way. You can draw it like this, okay, or we can draw it using wave fronts. So what is a wave fronts? 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 So wave fronts will tell you that on the same fronts here, or here is another wave front, or if you have another period here, here is also a wave front. What about the properties of the wavefront? This is a question. Anyone can help me to answer this question? No. So I will call Châu, Phạm Hà Châu.
Can you wait a minute? I don't think I know about this that well.
I think the wavefront is like we represent the wave through its peak. And we just like draw the peak of the light of the light wave instead of like drawing a straight rays. I think so.
In fact, you can imagine the wavefront is a surface. Okay, is a surface that depends on the point in that surface are in phase, have the same phase. Okay, I will write it. Okay, on the point. Okay, in fact, you can use this front is okay. Is also this and this are also wavefront. Okay, but we just don't want to choose the certain points on the waves. So normally we choose this one. Okay, but easier for you to describe it. It's okay. Why? Because the middle point between two front here will be the truth. Okay, here you see. So let's choose the smart way. Okay, keep in mind that front here is the surface, where all the point in this surface are in phase. Is okay. Here is a second way you can use to describe an electromagnetic wave. Okay. So if the source here is just a point, so front wave will be like this. Is a curve like, in fact, it's line like this. It's a circle like this. It's not a circle. So sorry, it's sphere. It's a sphere like a ball. Okay. But here I just this figure is just shown in the 2D. But in fact, it is a sphere. The blue one here. Okay. So here is a planar optical source. Okay, light from the sun so far from the earth. So we can consider that It's a planar wavefront like this. Okay, it's not a sphere, but this planar surface. Okay, the third way we can use to describe an electromagnetic wave is what? By rays. Okay, so if the electromagnetic wave like this is move in these directions. Okay, so you can use this, the direction the wave propagate will be as a wave. Okay, sorry, a ray like this. Okay, the direction of the propagation of light is okay. We have three common ways to describe the way to plot the wave. Okay, you understand it? Now you have to understand what is the light, some properties of the light. It is a wavelength, it is a frequency, it is a velocities. Okay, and how we describe it. Okay, three ways. So now we move to the next one. Okay, so here we will see what happens to the property of the light when it transfers from one medium to another medium. In this case, I have two mediums. This one is vacant, and the second one is another mediums like water or something else. Okay, not vacant anymore. So keep in mind that for the light, we have three basics, very important properties. The first one is wavelength. The second one is frequency, or 1/t. T here is the periods of time. Okay, period of times, and the velocities of the light. Okay, three important properties. Okay, so the way we determine wavelength, you know, okay, because it's a wave, so between 2 points here is a wavelength. Okay, or maybe between this point and this point you will have the wavelength, or maybe between this point and this point. 2 points have the two closest point which have the same phase, right? What is the velocities? What is the velocities? What is the velocity? And what is the t or f? T is the time. Is the line go from here to here? Okay, it finish one wavelength, right? It's t. F is over 1/t. Okay, and v is velocities. Okay, how fast the light move from here to here. You understand it? Three very important properties. And when it moves from the first medium to the second one, keep in mind that frequency doesn't change. Okay. Someone asked me the reasons why. In fact, you have to move to the maybe EM to BEM to. I hope Dr. Hung will explain it in EM1. I hope. But if someone would like to find out the reasons why frequency doesn't change, they can read about the boundary conditions. Okay, it's related to what happened at the interface between two mediums here. But now we have no time for it. Okay, just accept it. Frequency doesn't change. It will be the same. So the relationship between those properties is F equal velocity over wavelength. Okay, so if frequencies doesn't change, so if velocity decrease, the wavelength should decrease too, because frequency doesn't change, right? Right?
Yeah.
Okay. Okay. Keep in mind this information very important. Okay. If you know it on these other property, you don't need to remember. You understand. Okay. So frequency doesn't change. F here and F here will be the same. Okay. But keep in mind that here is the vacants. What happened in the okay? The velocity is here. We use a special symbol. It's C. Only for the velocity of light in vacuums. Okay, we don't call it V, the normal one, but C. Okay, and when it travels in another mediums, the medium will slow down the velocities. Slow down. Okay, so C is the maximum in all the other mediums except vacuums. The velocities here of the light will be slowed down. Okay, how much is it slowed down? It will be equal the maximum value here divided by the reflective index of the mediums. Okay, okay. So the same for wavelength, because here V decrease, wavelength decrease, so V decrease n time. Wavelength have to decrease n time too. So that frequency doesn't change, right? Okay. So here is the properties of the light, and also some how property change when it transfers, when it moves to another mediums. Okay. So now we will jump into the first problems. I choose here to practice. Okay, I will give you 2 minutes to read it. Any questions about the first part, property of light? Anyone? You have no question, right? Okay, so yeah. Someone want to say something? You see here is eye structures, and I have to say that to me is I don't know all the parts of the eyes. Okay, many things. Okay, and normally maybe you learn from grade maybe 11th or maybe 9th at high school or middle school. That you can just where my pen. Okay, draw the eyes this way. Okay, where we have the lens here, the lens here. Okay, we have the cornea here to protect your eyes. Okay, and here is the lens here, the white one here. Okay, and the light will come through this. Okay, because it is a lens, so it will create an image here. Okay, the image should be on the light here go through the lens through the vitreous. It's not the vitreous body, but vitreous fluid. Okay, gels fluid here inside. Okay, and the image should focus on the retina here. Okay, effects on the retina, you have pros and cons. Okay, if I remember correctly, the rod here will process the white and the black, and the con here will process the colors. Okay, and then it will convert into the electric signal and send to your brain through the optic nerve here. Okay, this optic nerve will connect to the brain. Okay, and then you can know the color and the dimension of the object you see. Okay, so anyone can help me to solve this problem. So the vitreous fluid here have okay, wait for me a little bit. So the index of the fluid inside the vitreous body here n will be equal 1.34. Okay, and the light range in the wavelength is from this to this, come to your eyes. Okay, with the wavelength is like from this. Okay, here is a range of the wavelength of the light come to your eyes. Okay, and the light here will get into your vitreous fluid, and they ask you about the wavelength and the frequencies. Okay, and the speed. You see three important property of the light: wavelength, frequency, and speed of the light, just as it approaches the retina here. Okay, here, okay, you see outside here, you know about the wavelength. Okay, you know about the velocity, and you know about the frequency of the first mediums, right? Of the first mediums. And when it enters the second mediums, they ask you about how these properties will be changed by the mediums. Okay, you know n. Okay, so Dương, can you help me to solve this problem?
Try to calculate the wavelength.
Okay, first.
We have violet thì 380 nanomet thì
how you can calculate the
So at first I have to exchange the violet into I will call it lambda 01, the violet wavelength.
Wait a little bit. Wait. I put them with my pen. How I open it? You still see my PowerPoint?
Yeah.
Wait, I don't know why how I can't hide your list of the students because it's cover my screen. Wait me a little bit. Okay. So can you repeat, please?
Okay. And in the exercise we have the wavelength in the air. I mean violet 380. We will call it lambda 01.
Icon is lambda v stand for violet. Is okay? It's equal 380 nanometer.
Yeah.
And lambda for red, right? 750 nanometer.
And now we have to calculate in index of reflection in the human eyeball. So we have the formula, the lambda equal lambda real 1 divided
So
by n.
in general, we have the solutions, the relationship between the lambda and n. Okay, and lambda will be
Lambda v
lambda. I call
divided
is
by
the
n.
lambda is the first mediums. Okay, here is the second mediums. Here is the
Lambda
first
v
medium divided by
n.
and I can the same with this, right? Here
Yeah.
air, right, will be n1. Okay,
Yes.
1 for the first, 2 for the second medium. So
So we got lambda 1.
lambda what?
Lambda 1.
I call is one here, okay?
Yes.
Or maybe one here easier for you to just to say, okay? So here the lambda here in the first medium, when it moves to the second, transfer to the second mediums, it will be changed, right? Because now we change the index of the refraction. How it change?
Let's call it lambda 2v equal lambda v
1
divided
in the first mediums over
by n, which means 1
n2,
point.
right?
Yes.
Okay, is equal
280 divided by 1.34.
2 minus n 2 okay.
Ta đây để em tính rồi.
Cô tính cô không tin thế nào rồi. Chúng nó kiện cô quá trời luôn. Calculator.
284.
Ra từ. Okay. 283.6, right?
Yes.
Okay, so you see that if the wavelength in the air is 380 nanometers, okay, when it transferred to these mediums, it reduced to 280.6 nanometer. Okay, it is reduced. Okay, and we do the same for the red light, right?
Yes.
So the lambda of the red light in the second mediums will be equal
Lambda 1.
the wavelength of the red light in the first mediums, right? Divided by the index of refractions of this medium, right? And is equal
559.
Great, I need to do it myself. 238, right?
No.
No. I'm so sorry. I devised my wrong number. It should be higher. 300 and my pen. 359.7, right? Nanometer.
Yes.
Okay, so but they ask you about the range, so you have to have the conclusions. Okay, so the range of the wavelength is from this to this. It's okay?
No.
It's okay?
Good.
Okay, now we move to the B part, the second part. Let me note down your name. Hoàng Dương, right?
Yes.
Student code, please.
So,
Behind 12.
no. 120.
Okay, I really want to give the chance to more students. So maybe someone can help me to solve the second problems when they ask you about the range of the frequency. Another student? Okay, we have 3 volunteer. Okay, let's see. Cấn Trung Hiếu. Wait. I prefer the new ones. Maybe I should check in the list. Hoàng Dương. Cấn Trung Hiếu. Okay, Cấn Trung Hiếu. It's okay. Vì bạn này bạn đã có điểm active ở phần trước rồi. Nhưng mà object cũng là phần khác. Okay. Wait a little bit. Where am I? Okay. Cấn Trung Hiếu, please.
So to so the frequency we use the formulas F frequency equal to V over lambda.
V over
Lambda.
Okay, but they ask you about the range of the frequency of the light inside here. Or just ask across the retina here. Okay.
So in this case, the V will equal to C and equal to 3.
I have a question. As I tell you before, here they ask you about the frequencies, the range of the frequency of the light here, not outside, not in the air, not in the air. So why you see here?
I think it's
right. Then you got the frequency of the light just as it approaches the retinas. Okay, within the vicious humor, they didn't ask you about the frequency of the light outside. So how can you see here?
I think the C here because it's a range where the frequency is the same in any medium is as a source in the same.
Yes. So you have to write down these statements before you use the functions. Okay. So we have to say that the frequency range in the air will be the same with the frequency range in the vicious humor.
Yes.
Okay. It doesn't change first. Okay. And then you can have the frequencies of
F1. F1
or F2 is the same. So you don't need 1 or 2. It's just violet. Okay.
Equal to C over lambda.
Lambda violet.
Lambda violet.
But here you have to use 1 because lambda change. So we have to, because here we have lambda for violet 2, lambda for violet 1. Okay, for the first medium. For the second medium, so we have to write out 1 here. Okay, because it changes when it transfers to another mediums. It's okay.
Okay.
Tell me the result, please.
It's 7.89 multiple with 10 power of 14.
14?
Yes.
Okay, like this, right?
Yes.
Okay. Unit, please. Hertz. Okay.
And we calculate the F of red.
Okay.
Equal to C over lambda 2, lambda red, and is equal to
lambda 2. Why you use a lambda?
Lambda.
Because C and V should have the should be the property of the light in the same mediums. Here is C is air, so should be the wavelength in the air too. 1 red. Okay.
Is equal to 4 multiple with 10 power of 14 hertz.
That's right. So
Yes.
the range of the frequency should from this to it. Okay.
Yes.
Okay. It's good. We can't apply these equations for the second mediums because we don't know about the velocity of light in these mediums. Okay. We don't know about velocity of light in this medium. So, but luckily we have the information that frequency doesn't change. Okay, so let's calculate the frequency of light here, and then you will know the frequency of the light in the second mediums here. Okay, so the C part, here, right?
Yes.
Because your name is so special, so I think I don't need the student code. Okay, so another one. Another one for the last part. Okay, many one raise hand. Okay, so I will call the second ones. Nguyễn Đăng Sơn. Keep in mind. So keep in mind that if you have already your active bonus, okay. So let's give the chance to another one. Okay, just in case no one raise your hand. Your chance. Okay. Okay.
So here we have this calculated speed of light just at an approach the retina. So here the light has traveled from the air to the
viscous
fluid.
Fluid. Okay.
So I'm gonna use V is equal to C over the index of refraction of the fluid.
V equals C over
N. If it's
N?
if it's the
because here I have one N1 for the index of refraction of air and N2 for the viscous humor. So
it will be N2. Yes, it will be N2. Okay.
Okay. So you know about C, you know N2. You can know about the velocity, right?
Yes.
Another relationship, if you know.
Another relationship is I have V times N2 is equal to C times N1.
Or maybe this, because now you know the wavelength. You know about the frequency.
Or I can use that relationship.
Okay. Or maybe you can use another function here. V equal lambda.
F.P. F lambda. Yes.
F lambda. Okay. But I think this way is much better. Okay. Because C is a nice number, and also here is not a 10 to power blah blah. Okay, it's a nice number. So now
the answer is 2. Let's see, the number is too big. 3, 6, 9.
So it's going to be 3 divided by 1.34.
So it's gonna be 200 millions. I'm just gonna put 2.2 times 10 power over 8. Yes.
8, right?
Yes, it's about that number.
Okay. So you see that if the velocity of the light in the air or vacuums is the same. In physics, okay, normally in the air is in the vacuums, and here's the n, okay, 1, okay. So it will be reduced from 3 by 3. Oh, I just erase it. It reduced from 3 10 times 10 to power 8 to this value. Okay, it reduced. It's okay. So by these problems, I just remind to all of you that keep in mind 3 important properties of the light: wavelength, frequency, and speed. Okay, and frequency doesn't change. Okay, frequency doesn't change. Okay, so now we will move. Any questions? Sorry, I forgot to note down your name, please.
It's Nguyễn Đăng Sơn.
Nguyễn Đăng.
Nguyễn Đăng Sơn.
Cô nghe không rõ luôn.
Nguyễn Đăng ạ.
Nguyễn Đăng Sơn à?
Vâng, Nguyễn Đăng
Nghe
Sơn.
khó lắm. Đăng Sơn. Okay. BI 12.
386.
386. Okay.
Yes.
Okay. So, any question about the property of light? No, right? Because I think it's not too difficult. Okay, so now we'll move to the next part. Okay, here we learned. Here is you see. Now we know about the light. Okay, here is the light. Okay, and when you look at this, you see that here is one of three ways to describe a light. They use a ray. They didn't use something like this, or maybe didn't use a front way like this. They use a ray to describe a light. Now you have to understand. Okay, and you know that these rays have some properties: wavelength, velocities, and frequency, and so on. Okay, and now where is the interface? Here is interface. Here is interface. Okay, we have the interface here between two mediums. Okay, so from this part, we will learn when the light sees interface, what happens? Okay, at the interface, the first phenomenon we learned is reflection. Okay, and the second one is refractions, and then we will learn about the diffractions and interference. Okay, many things, many phenomena happens. Okay, we go from easier and to more complicated phenomenon letters. Okay, so first, law of refractions. Here is the law. Okay, they said that here is the incident beam or incident rays come to see an interface. If it's reflected, so the angles of the incident beam with the normal will be the same angle with the reflected beam with the normal one. Okay, normal here is the one perpendicular to the surface. For sure that you are much better than me to remember those equations. Okay, here is the law of reflections. For the law of refractions or law, okay. In fact, in my course for the EM2, maybe for the SA students, if you are here, AMS and EPE students, okay, they will learn more deeper into this, and I can explain and prove why do we have these equations by using the boundary conditions. But in this course, or maybe at high school, you just remember it. Okay, you have to accept it without explanations. Okay, I think it's not fair for students, but you have more time and you are interested in this field, you can reach yourself and find the textbook somewhere to explain it. Okay, because to explain it, we need more than 30 minutes. Okay, so for the law of refractions or Snell law here, you need to remember relationship. Okay, so keep in mind the way we determine this angle. This angle, okay, is the angle between the ray and the normal one. Okay, and the normal here is the first point you need to remember. The second point is the index of refractions of this medium have to multiply by sine of angle of that mediums. Okay, and it will be like this. Anything else you need to remember? I think that's all. Okay, So now we'll move to any question about this part? I think there are no question. Okay, should be, because you just need to remember 2 equations. Okay. Okay, so now we'll move to the first problem related to this knowledge, and then you can practice. In fact, this problem, you just need to remember the equation of refraction, because we don't have the reflection in these problems. But refraction a little bit complicated, right? So in these problems, we have a layer of waters. Okay, here is waters, and here is X materials, okay, in a beaker, and the rate of light traveling upward, okay, from this point, and it travel upward like this, okay, for the part indicated here, okay. And they ask you about the index of the X materials. So when you look at the equation here, you see that this equation is so important when you would like to determine the index of the materials. Why? Because normally when you have 2 mediums, the first medium here, the second medium here, right? And if the first one is air, for example, okay, and you know about in the first medium, you know about the index of refraction, N1, okay, and you need to determine N2. Okay, so this equation is very important. Why? Because normally if you have a light, okay, you have a light source like this, okay, so easy for you to determine the angle. So easy for you to determine the angle. So you know about this. And it's so easy for you to measure as well this angle too. For sure. Because you just use the color light, okay? And then you can measure it easily. And if you know the index of the first medium, you can determine the second one. Okay? So this law is very important for you to determine the index of the refraction of any mediums. Okay, it's a way to measure us. And it is exactly these problems. Okay, they ask you to determine the index materials X. Okay, so in this case, they didn't give you the index of the refraction of waters, but normally it's famous, right? Someone can tell me? I call is A and X. Okay, and air is A and B here. And B. What is the index of refraction of waters?
Uh, 1.33.
33, right?
Yeah.
And what is the index of refraction of the air?
Is 1.
Yeah. Okay. And X, we don't know it. Okay, but you see, we can determine the angle here. We can determine the angle here. But keep in mind, as I explained before, the way we determine the angle here should be the angle between the rays and the normal. Okay? The ray can be the incidence ray, reflected wave, or refracted wave. Ray, okay? Because here in the figure, they have a trick, right? Because here is a normal one, but 65 degree here is not the right angle. The right angle should be like this, okay? So, the first problem, someone can help me to solve it, please?
Can I do it?
Wait a little bit. Blah, 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 blah. Okay, tell me your name, please.
My name is Nguyễn Anh Quân.
Anh Quân. I need to save my document. Anh Quân. Pen mode. Oh, what? VI12?
365.
Okay.
Okay, at first, we need to find the incidence angle of x,
Okay.
which is
Okay.
which is equal to 25 degree.
So I call it what? What symbol would I give you?
Theta a.
I
No.
don't want to A.
Oh, theta x.
Theta X, okay?
Yeah.
Okay. I can have the name here, maybe theta A, okay?
Yes.
Okay. So
Theta x is equal to 25 degree.
the incidence angles, okay? Theta X will be equal 90 degree minus 65, okay?
Yeah.
Okay.
And then we apply the Snell law to find the index of reflection of x.
We have
Nx multiplied by sine theta
theta
x is equal to Na multiplied by sine theta a.
okay. You know it, and you just need to calculate it. So Nx will be equal, right?
Yeah. 2.33.
No.
Just
Wait.
the formula.
Always write down the formulas, okay?
Yeah.
And now can you give me the results?
It's 2.33.
2.33.
33. Yeah.
Okay, I believe in you because I don't have my calculators here. Okay, so it's easy, right? First one.
Yeah.
The second one, someone else? Sorry, anh Quân. Okay. Anh Quân. Nhi, okay. Đoàn Hoài Nhi, okay. Wait. I need to note down. Nhi. BI 338, right? Okay. First, because here I note on the symbol on the figures, okay? But it's better if you can explain what you want. Okay, because why? Because from the first section related to electricity and magnetism, I see that many of you just write down many things, but when I look at the figure, I don't know what you want. Okay, so keep in mind that please explain everything, and the figure, the content in the figure should go with the content in the text. Okay. Okay, it is a recommendation for all of you. Okay, so you should explain the theta B will be blah blah, theta A will be blah blah. Okay, you should explain here. Okay, so now just that. Can N be sine theta B theta A, right? Theta A So because this normal and normal is the same, okay, and parallel to each other, so its angle also equal this angle. Okay. So I think first you have to state that at the interface between water and the air, theta A will be equal blah and A will be equal blah here, okay? And B will be equal 1, okay? And then apply the Snell law. We have this, okay? And because you know it here, you know it here, you know this, and you need to calculate this, right? No, equation first. Can you repeat the result, please? 0.90 99. Really? Okay. So you find out the theta b equal. Okay, almost 90 degrees. Okay, so here for these fractions related to the reflection and refractions phenomena, you just need to remember two equations, okay? But keep in mind the way we determine the angle, okay? This is the first point you need to remember. Own way between the normal and the ray, okay? The first point. And for the Snell law, the angle of that mediums in that medium should go with the index fractions of that mediums. Okay, keep in mind that. Okay, not too difficult, right? So now we will move to the next one. Let's see what is the next one. Okay, total internal reflections. Okay, here back to this equation. You will see that here is the interface between two mediums, right? Here is the interface between two mediums, the medium A and the medium B. Okay, and they said that the totals internal reflection occurs only if NB is smaller than NA. Do you know why? Do you know why? Yeah? Someone raise your hand, right? You want to say something, right? Do you know why you should have this condition? Okay, let's see.
If NB is bigger than A, then the sin will bigger than 1. So it's not.
Yeah. Based on your answer, I see that you see the problems because from Snell law we said okay, here is a medium A, so you have the why it happened like this? You have the NA of this medium multiplied by the sine theta A, right? Theta A here equal NB here multiplied by sine theta B, right? What does this mean? If the NA bigger than NB, okay, so the sine theta A will be smaller than sine theta B, right? It means theta A will be smaller than theta B. Then there is a chance where you can see the total internal reflection. Why? Because here is a theta A, here is a theta A. Okay, so when you increase the theta A, increase, you see the angle increase. Maybe here is 30, here is maybe 45, here maybe 60 degree increase. And when we increase the theta A, increase, so the theta B should be increased as well. Okay, okay, and when the theta B equal 90 degree here, okay, is where the total internal reflections start happening, right? But if the NA is smaller than NB, what does this mean? NA larger than NB. So even if the theta A equal 90 degrees, okay, the maximum, the theta A here in 90 degree is maximum, then no chance for delta B higher than 90, right? Never, because it's smaller than theta A, so never is happen. It's maximum, it's just like this, never larger than 90. So the total internal reflection occurs, never occurs. Okay, so that's why here should be the first conditions for the total internal reflections occur. Okay, it's the first. The second condition is when the total internal reflection occurs, when this angle start to be 90 degree, and then it just need to be higher than this, then you will have the total reflections, total internal reflections. Okay, so you should need to apply the Snell law. Okay, the angle here we call it the critical angle because it's important. Okay, here the angle here. Okay, and this angle is just need to be higher than this, then you will have this happen. Okay, here is a total internal reflection. Okay, so you have the, if this is an increases angle, so the theta B should be 90 degrees, so it should need to apply the Snell law, right? Sin of 90 degree will be equal 1. Okay, and we call the angle where the theta B equal 90 is theta criticals, like this. Okay, criticals angle like this. Okay, just change the symbol, nothing important. You can to me you can call it theta A, is no problem. Okay, it's just a name. Okay, and then you can find out this will be equal NB over NA like this. Okay, everything is from Snell law, and in fact we can call it is a special case of refractions. Okay, and in fact in the daily life it's very important. Okay, because if you remember, maybe we have a toys, maybe in my I don't know how to call it toys, but you have a line here, okay, and have many plastic here, practice wire here, and you turn on the light and you can see the light at this point. Or maybe now you know about the ear picker. Okay, normally you have this. Okay, you put it into your ear and pick something dirty. Okay, and now if you have the light here, okay, you turn on the lights and you have the light at another end of the picker and input it inside your air, maybe for the children. It's very nice one. I use many times. Okay, very important application. And the most application of this phenomenon, you know that you have the optic fiber or fibers wire like this. Okay, and the light, the electromagnetic wave is information. It brings inside its information. Okay, and if you transfer it in the fiber wire like this, it just go inside. It doesn't get out of the wire. Okay, so it can transfer from this end to this plate to another plate. You see, very important one. But keep in mind that here, you see, this angle depends only on the index of the refractions between two mediums. This medium and the mediums where you put this in. Okay, so keep in mind that this angle, if you put this device in the air, will be different when you put it in the waters. Like you have some fire wire, and put it in the sea or the ocean. Okay, the angle here should be different. Okay, just depend on the index of refraction of the mediums A and B. Okay, so I think it's quite easy too. It's just a special case of refractions. Okay, so now I will move to the next problems here. And I give you maybe 2 minutes to read it. I need to read it too. The critical angle for the tablet. Someone. Sao cô nghe thì tiếng tinh tinh gì nhỉ? Các bạn nhắn gì cô à? Okay. Read your problems, and after 2 minutes, some of you can help me to solve it. So we have the interface between a liquid and the air, right? Okay, Phùng Đức Thái. Thái chưa giơ tay lần nào đúng không? Okay, Thái, please.
So first, in the first problem, we have the incident angle is less than the critical angle, so that we still have the fraction, the refracted ray.
I have a question.
Yes.
The light travel from the liquid to the air or to the air to the liquid? From the air to the liquid.
From the liquid to the air.
Why?
Because here it said that the light traveling in the liquid has an angle incident.
Okay, or maybe it's another reason.
The refracted ray in the air. You said?
Because we have the total internal refractions. It means the light have to travel from the mediums which have the highest index of the refraction. Right?
Yeah.
Yeah. Okay, it's just extra question to make sure that you understand the problem. Okay. So
we still use Snell laws. We have
we apply the first, when you solve a problems, you have to plot it on the diagram like this and tell the readers what the problems give you and what you need to do and something like that, right? To explain
yeah, so first we draw a normal line.
Normal line, okay.
Then the incidence ray, which is 35 degree.
What? 35 here, okay.
With a normal.
Okay. It's okay.
And
what is the next?
We have the refracted ray.
Reflected, if I draw it like this, it should be below or higher than this array.
It should be below.
Like this?
Yeah.
Okay. Okay. And
because we have critical angle will the sign of critical angle will be equal to the.
But you have to name the angle, right?
Oh
easier
yes,
for you. Yeah, easier for you to use a function.
Theta B.
Theta B.
Yeah, and the other is theta A.
Yeah, theta A. Okay. Okay, so first, I think if I were use, I will say that because part A, okay. If you say some nice words, I think Dr. Cẩm will be happy. Okay, so because the incidence angle is 30 degrees lower than the critical angle, so there will be the refractions happen, right?
Yes.
Is the first point. Okay, and then you call theta A is incidence angle, with theta A will be equal 35 degree. Okay, and theta B will be the refracted angles. Okay. Yes. As indicated in the figure. You see? Okay. Okay, you have to say that. Okay, and then you apply. You said that you apply Snell law, right?
Yeah, it's Snell law.
Okay. Then
the sign of theta A multiplied by
NA.
Yeah, NA.
Yeah.
Sine
Sine
theta A
theta A will be
will equal
equal
to the
NB, right?
yeah, sine theta B.
Sine theta B. And they ask you about the angles
B.
of the refracted angles, right? With
Yes.
the normal. Okay. They ask you
So
about
calculate the
this.
sine theta B.
So sine
Sine
theta B
theta
will be equal NA and B sine theta A. Okay, now your job.
And because we have a sine sine of critical angle will be equal to the NB over NA.
Wait. I'm looking for the index of refraction, because here in this case air we know it is equal 1, but this we don't know it. We know this, but we don't know it.
Yeah, but we know the friction of NB over NA.
So we have to calculate the NA before.
No, we apply the formula sine sine theta critical equal to NB over NA. So we just like divide by that.
If I were you, I would separate them from each other. You know why?
Why?
Why? Because if here is just for the exam, okay? So if you put on step in one, if you have a mistake, you lost on the mark, okay? But if separate into first one, the second step, so each step you wrong, you still have point from the first part. You understand it? So don't put all step in one. Okay?
Yes. So we will separate it.
Yeah, you should. Okay, because if you have problem with this step, okay, you replace it with wrong idea, a wrong results, you lose all the point. Okay, so
Yeah.
first, it should be something first. Okay, here.
We calculate the index of
Okay, so you have to say some word. When the totals internal refractions occur, okay?
Yeah.
Blah blah. You have what?
We have
A multiplied by
sine
theta with equal criticals,
yeah.
okay, will be equal
B
and B sine 90, right?
Yeah.
Okay.
Which is
okay, so
1.
Find out NA, because here you know it equal 1 and B equal 1. Sine, you know this angle here is 42.5. So we can know NA.
Yeah.
Okay. Tell me the result because I don't know.
Is equal to 1.4.
1.4.
48.
Like
so 1.5.
1.4.
1.48.
48. Like this.
Yeah.
Okay. Okay. So you have to put this step before. Okay. Okay, and then you apply Snell law. Now blah blah, it will be NA over B. Okay, and it's equal 1.48 over 1 multiplied by sine theta 35 degree. It's okay?
Yeah.
And then you find out theta B equal?
First, the sine of theta B is equal 0.84.
0.84?
Yeah.
So
theta B will be equal 58.1.
58.1?
1 degree, yes.
Degree. Okay. So you see, when you look at the problems, first you have to show it in the figures. Explain what you want. Okay. And if you need 2 steps to solve the problem, let's separate them. The reason I just give you. Okay. Don't put all of them in one, because if you have a mistake, you will lose on the point. Okay. Okay. So here the first one. Okay. The second part, Thai, right?
Yes.
Phùng Thái, right?
Yeah, Phùng Đức Thái.
BI
12 396.
396.
Yeah.
6. Sorry for my letter, it's too bad. Okay, the second part. Let's read it. I didn't read it. Yes. If a ray of light traveling in the air. Okay, in the air has an angle of incidence at the interface. What does the angle derivative makes with the number? Okay, someone can solve the second one for me. So you see, as I explained before, total internal refractions. Nothing than a special case of the refractions, right? It's just a special case. So you just need to apply Snell law because there's nothing more. Okay, just only one equation for you to remember about the phenomenon Snell law. Okay, someone can solve these problems. No one? No one? Ủa, tại sao hôm nay lớp mình ít thế nhỉ? Hôm nay có 30 bạn thôi à? Ok. Đi đâu hết rồi? So now I will take a pictures. Controls. Done finally. Okay, I just take the picture to check your attendance letters. Okay, that to right, raising your hand. Okay, let's see. Phùng Đức Thái, no. Chu Bảo Minh. Okay, you can solve the second one.
I think we apply the equation, but different angle is NA with sin theta B is equal to NB sin theta A.
Okay, and then now. Yeah,
so
now the ray is traveling in the air. Okay, have this incidence. It means the ray now is travel from the air to the
air to the liquid.
To the liquids, right?
Yes.
Okay, you have to say that. Okay.
Okay.
The light is the ray of light. In this case, it travels from the air to the
liquid.
Liquids with the incidence.
With the incident angle is 35 degree.
You call it theta B in this case. You don't need to change the name. Okay, it's just set that the incidence angle in theta B will be equal 33 degree. Okay. Okay, and you call theta A will be the refracted angles. Okay.
Yes.
But angle is between this and that. Okay. So we have to say that the theta A is a refracted angle between the reflected ray and the normal. Okay.
Okay.
And apply the Snell law. You will have what?
I will have N B sin theta B equal to NA sin theta A.
Sin theta A. You know this. You know this. You know this. They ask you about this, right?
Yes.
So sin theta A will be equal NB over NA sin theta B. Okay. The result, please.
So the result is
NB in this case is 1, okay, and A is
1.48
1.48 multiplied by
sin 35 degree.
equal.
So I use the calculator and I calculate the theta A directly.
Okay.
So the theta A is 22.8 degree.
22.8 degree. Okay. Okay, you see, refraction or total internal refraction is to me quite the same. Okay, just special case. Okay, so now we move to the last one, polarization. Okay. I have 50 minutes. Okay. So here I prepare some figure for you to practice this. Okay. So you see here, here is a light. The blue, I don't know, the purple one. I don't know how to call this color. Okay, you see here. I use the first way to describe the wavelength. Okay, so here is the first way. Okay, and here is the second way. You see? You understand it? Okay, so I have two waves. Okay, so keep in mind that you have to understand a single wave. Sorry, the wave with the so yeah, we can call it single wave. So now if you have a single wave, I consider the first wave the blue one. Okay, change the color. It's like this. Keep in mind that the electromagnetic wave have two components, electric field and also the magnetic field. But for the opticals, we just care about the electric field components. Okay, and we can plot it like this. Okay, and you see that here at this point you have the magnitude of this field. Electric field is like this. At this point is higher than this with this direction, upward direction, but its positions the electric field at this point downward like this. Okay, and the magnitude of it is changing like this. Okay, so if you have a single wave like this, okay, and you stay at this position, okay, you stay here and you open your eyes. Okay, open your eye here. Okay, open your eye here. Here is your eyes at this position, and you look at the wave. You look at the waves. Okay, you look at the directions and the magnitudes of the electric field. So tell me how it look like. You look at the magnitude and the directions of the electric field. So what did you see? You see that? You see? this. Okay, you see that the electric field is up and down, up and down, up and down in only these directions. You see, you look at this, you see the direction and also the magnitude of electric field here. You see that, right? And here is the way you describe the polarizations of a light, okay, of a single wave like this. You understand it? You understand this?
Yeah.
And here is a polarization. Okay, each have another name is linear polarizations or polarized light. They call it is a polarized. Yeah, polarized light. This light is called polarized light. Okay, because it's only have this one direction. Okay, so now if you understand about this line, let's come to this sonority to see. Okay, now in this case I have two electromagnetic wave. Okay, and the first wave is blue like this and the second one is purple one like this. Okay, and they are perpendicular to each other. Okay, so you are stay here and you look at the light. Okay, in fact, at any point here, because electric field is a vector, right? So at any point here, you just need to sum up two waves together. Two electric field at any point together. For example, at this point, I will change the color. I have this for the first wave. Okay, the purple one here E2. It's like this. Okay, so the next one we just sum up them together at this position, right? You get this one. For example, at this point, okay, the first way you have this, the second way you have this, so the next one will be like this. Do you agree? So when you combine them together, you will get it. Okay, you will get it. So if you look at this position and look at the wire, look at the light, what you will see? What you will see? You see that here I draw a circle here, like, okay? You see that now the direction of the polarization is not straight one like this, but like this. Okay, because now the electric field is like this. You see, it's just in this direction, and go up in this direction. Okay, it's just move back down in this direction. Okay, so now will be the direction of the polarization in this case. It's not straight one like this. Let's make an angle to the normal. You understand it? You understand it?
Yes.
Yes. Okay. So we come to another sonority to see. We still have two waves, but in this case they are in phase. In phase, what does this mean? It means that the maximum of this line will be the same position with the maximum of another line. The minimum ones will be in the same position. Okay, they are in phase. But in this case, one of them are ahead of each other, so they are not in phase anymore. Okay, so for example, if you make the sum of this, okay, this one will have this one will have this, so the next one will be like this. Okay, for example, at this position, this one will like this one will like this, so the next one will be like this. Okay, so if you sum up the electric field of two waves together at any position, you will get this results. You see the red one here is when you combine them together, you will get this one, the red one here. Okay, so if you look at this light at this position, what you will see here? What you will see? How about the polarization here? How about the direction of electric field in this case? You see that it have all the direction. What the heck? What? Okay, so if you look at this position, you look at the directions and the magnitude of the electric field of this wave, you will see that it have all the directions. You see, this direction it have, this direction it have, this direction, all the directions. Okay, so that's why you have here all the direction. Okay, and in this case they have the same magnitude because the first wave and the second wave here have the same magnitude. Okay, so that's why it is circle like this. Okay, and the electric field of the next wave have the own direction. So in this case they call it unpolarized. Okay, unpolarized light have no specific direction, own direction. So we have it, we call it unpolarized light. Okay, so you see that in fact unpolarized light is a contrast of polarized wave. You see it contrasts of the first one here is the polarized wave. Do you agree? The second one here is also the polarized wave. Okay, but when we combine them together, you get the unpolarized light. Okay, so that's why here I note down unpolarized light is a contrast of polarized electromagnetic wave. Okay, so now you have to understand this. You have to understand it. Okay, any question about this? You understand? In this part, first you have to what is the polarizations. Okay, and you have to understand why they plot it like this, why they plot it like this, why they have this figure. It's so weird. Okay, in fact they have another kinds of unpolarized, not a circle like this, but ellipse like this. Okay, we have it when we have the wave here is not the same magnitude. Okay, they are not the same magnitude. So when we come to the combined wave here, the magnitudes not the same. Okay, but maybe Dr. Kam explains it's better than me. Here I'm just here to review the knowledge, and then you can understand better the problems. Okay, so any question about the polarizations of the light? You understand it? And what is an unpolarized light? You understand it, right? So in this part here I take some figures from the textbook. Okay, and I see that's okay. Here is a Malus law. Okay, let's see. Here you have the incident rays is unpolarized light. Now you understand what it is, right? What it is, right? You understand it? Okay, here is the incident beam, and it's come to see the polarizers. Okay, polarizers is a device, and let's imagine it is a picky fences like this. Okay, with many trickies. It's like a fence like this. It's because of the structures of the materials that's used to generate these polarizers. Maybe the I forget its name of materials, malolins or something like this. Okay, okay. You can imagine it's the fence like this. Okay, with the parallels one like this. Okay, and when the incidence unpolarized light get into this. Only the components which is parallel with the polar here can get through the polarizers. So that's why only these components is out from the polarizers like this. Only these components. Okay, and you have another the second polarizers. We call it the analyzers. Okay, we get into it. So you see that's the input of these polarizers. We have these polarizations. Okay, and we can combine. We can decompose it by two components. The first one is parallel, and the second one is perpendicular, like this. Okay, and you see here is the directions of the polarization of the analyzer. So only the components have the same direction can get through. So that's why only this component can get through, and this one no, stay there. Okay, so we have these components. Okay, here is I just explained what it is. The second one I would like to explain is intensity of the light. Okay, so if I call I0 is intensity of the light here, of the incident beam here, it gets through the first polarizations. Okay, and the intensity of the light here now is just I0 over 2. Do you know why? Do you know why? Do you know why? Do you know why?
Why?
No one knows. Why? Okay, you should ask me. Okay, in fact, we have to use the integration of something like that, but keep in mind that here I just explained briefly for you. Keep in mind that I have a question. If I have the unpolarized line like this, okay, and here is the incident beam, and it come to see the first polarizer with this direction of the polarizers. Okay, so same with this one, parallel with this one. My question is, how about this? How about this direction? It can get through the polarizer or not?
No.
No. A part of it can get through. Only the one that's perpendicular to it can't get through. Okay, only here, the direction here, keep it, I will repeat. Here is polarizers. Okay, all of this will get through this, and nothing of this will get through it. Nothing perpendicular. But for this one, a part of it can get through. Why? You can decompose it into two components. The first component is perpendicular to this. The second one is parallel. So the parallel component of this one can get through. Okay? A part of it can get through the polarizers. Okay? So if you take a if you just look at this, you see that okay. So a half of it can get through. If you take the average of it, a half of intensities of the incident beam can get through. Okay, it's just average problems. Okay, so here is intensity of the incident beam. So output from the first polarizers will be I over 2. Okay, so if you learn from the chapter 32, I don't know why they didn't teach you, but you know that the intensities will proportionally to the E square. Okay, E here is the electric field components. Okay, the intensity will be equal to E squared. So the electric field here get through the second one is just E cosine theta. The E sine theta can't get through. You don't need to care about this. But this one, yes. So how about the intensity here? I will be equal E square, right? E square multiplied by cosine square. Do you agree? Because it's like this. What is E square? What is E square? It's exactly like this. Will be equal E 0/2 multiplied by cosine theta. Okay. So when you look at the malus here, okay, the malus here, I maximums EI here. Okay, and I here will be I at this position. Okay, and the theta here will be the angle between the electric field of this polarized line with the direction of this polarization of the analyzers. Okay, so be careful the way you determine the angle and what is what here. Okay. So here I prepared a problem for all of you, but maybe we have no time to solve it because I take time to explain polarizations here. But I think it's not too difficult for all of you to solve it now. We have the unpolarized